So we're recording. We're talking about pages 3, 4, 5, 6, 7 of the section 5.3 notes. So there's a new topic or a new term, if you want to call it that, which is concavity. I'll explain concavity in just a little bit. But imagine that you have the following graph. By the way, this is y equals x cubed. You could see for yourself if you were to plug in points. And imagine drawing in all the tangents to the curve from negative infinity to 0. So like, I have a tangent line here. 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 What can you say about the curve here? We could say that the tangent lines are becoming less steep. In fact, the slopes are decreasing in value, right? It's very positive here. I mean, F prime is positive for sure here, and it's still positive here. And then F prime becomes 0 over because it flattens out. So it seems as though we're becoming less and less steep, right? So what can this happen to the derivative from negative infinity to 0? The derivative is going to be decreasing. So we see a change in the derivative. Keep that in mind. We see a change in the derivative. Derivative is a change also. So we see a change in a change. Keep that in mind just for a minute or two. Now, what if I drew in all the tangents from 0 to infinity on the right half? Well, they start becoming more steep. So now your tangent lines are becoming more steep. So in this case, the slopes are increasing in value. So you could say that what's happening to the derivative here, the derivatives are increasing in value. The slopes are getting higher. So again, we see a change in the derivative. So as long as your graph is differentiable, meaning it's smooth, you have a nice and smooth curve. And let me erase that. That's kind of hard to read. A change in the derivative. But we see different kinds of changes. To the left is 0, to the left is 0. From the interval from negative infinity to 0, we see that the slopes are decreasing in value, the slope of the tangent line, where then the slopes are increasing in value from 0 to infinity. So we call this whole phenomenon concavity. Concavity is this phenomenon of changes in F prime. That's what really concavity is. It's the changes in F prime. Now we say we're concave down if Y prime is decreasing in value. We say that we're concave up if Y prime is increasing in value. Another way to think of this too is that if the curve is below your tangent lines, you're concave down. So you can see how the curve here was below the tangent lines. So here we say we're concave down, or CD for short. Whereas here, our curve is above the tangent lines. So see my curve here is above the tangent lines. And so we call this part concave up, or CU, concave up. So you're concave up when you see a positive change in your derivative for an interval, where you see a negative change in your derivative, then we call it concave down. Hopefully that's intuitive. And so, no, when y prime is decreasing interval, its derivative is negative. And that's what we're trying to say there, is that when we talk about a change in a derivative is a change. So you're talking about a change in a change. And when we use the word twice differential, it means we're doing the derivative twice. So what we're really looking for in a concavity test is a second derivative. If your second derivative is negative, you're concave down. If your second derivative is positive, you're concave up. And the reason why is because, again, if f prime is decreasing, it's kind of like you're doing this, d dx of f of x. You're doing it twice. So this right here is some value, whatever. But then if that's going down, so basically you're doing the derivative of f prime. Like you're doing a change of the derivative. So that's what we call the second derivative. So if that second derivative is negative, you're concave down. If second derivative is positive, you're concave up. And really what you're looking for are slopes decreasing for concave down and slopes increasing for concave up. I also sometimes like to think of it this way. It's how I thought when I was in high school, but I probably shouldn't have thought of it this way because I just confused myself. But I like to think of this as like, this is concave down right here. It's kind of like a frown face because you're going down. And that's kind of like a smiley face because it's kind of curving up, if that makes sense. But really, it's more a matter of looking at the slopes. Are the slopes of the tangent line, so they're positive, but they get closer to zero, so decreasing value, concave down. Where if your slopes are zero, then they start increasing value, concave up. And of course, sometimes you could have, initially your slopes could be negative. Like, for example, here's a parabola, right? My slopes are negative, and then they go to zero, then they go to positive. That's still an increasing slope, or increasing values of the slopes. That's still concave up. So let's do the concavity test, for example, too, and use the proper language. And then we're going to talk about another thing called points of inflection, which is closely tied to concavity. Then we'll talk about something called the second derivative test after that. So let's do this, really simple. We're going to do a concavity test. Find f tilde prime. Set f tilde prime equal to 0. Solve for x. Sign chart. And when y, or when f tilde prime is positive, concave up. If f tilde prime is negative, concave down. So f prime of x is 4x cubed minus 12x squared. F double prime of x is 12x squared minus 24x. Set this bad boy equal to 0, factor out 12x. And you can call these critical points if you want, 0 and 2. Make a sign chart, 0 and 2. And you're testing for the second derivative, right? We want to see where that is positive or negative. If I plug 3 into my second derivative, I get positive. Plug in 1, I get negative. Plug in negative 1, I get positive. So I'm concave up from negative infinity to 0. And I don't remember if we do, I think we do open intervals for this. Yeah, you do open intervals because at 0, if your f tilde prime equals 0, you're neither concave up nor concave down. So we do open intervals here, always. So you're concave up from there and also from 2 to infinity. Where are we concave down? 0 to 2. There we go. Those are the intervals. The proper language is down here. Like if I were to type this up, let me go to a text box here and change colors. I would say F is concave up in the interval negative infinity to 0 and, or actually it should be or sorry, I meant to say, yeah, that's right, into infinity, because F double prime is greater than 0. And I'm going to get lazy and say in those intervals. You should restate the interval. There you go. That's the proper AP language. And then you would just say the same thing for a concave down. All the questions in the chat. Oh, great question. Why is it or instead of and? I'll get to that in just a sec. When making the sign chart, do you plug in the values? Yes. When making sure you plug into the second derivative, not the first. You plug into the second derivative because you want to see the sign of the second derivative. That's how the test for concavity. Do not do the first. And then the question is why did I use the word or instead of and? It's not and because and is an overlap. So this is going back to set theory, which is kind of maybe it's covered in middle school. I don't know when you guys, or maybe even if you guys cover it. But if you have something like this here, if you have like 1 to 4 and 5 to like say 6, this right here is or, because you can't be in both of those at the same time. You can't be at two places at once, right? Either you're here or you're here. X cannot be both between 1 and 4 and 5 and 6. Like if that, so you say or, so X is either between 1 and 4 or 5 and 6. So like X is like 2.5, great. It's one, not the other. Or X is 5.5, great. It's not one, not the other. You gotta say or when you're using a union. You cannot say and. And is an intersection. We use and, like for example, let's say you have, and this is going back to set theory, like say you have like 1, 2, 3, 4 as a set of numbers, and you have this right here. So this is an and situation. We call or an intersection. In this case, you're looking for an overlap. That's 2, 3. We don't really deal with this in this class. We don't, but that would be an and situation because you want to be here and here. You want to be in two of those places. You want both of these things. So you got to say 2, 3. So great question. Because yeah, a lot of times people don't really question that. I'm glad someone did. Okay, let's keep moving. Points of inflection. And I think yeah, let's talk about that, and then let's do second derivative test, and then we'll take a break there. Points of inflection. It's where the concavity changes. So a point of inflection is when y double prime, or we'll say f double prime, just to be consistent, f double prime changes sign. You need to see y double prime change sign. So not necessarily when f double prime equals 0, even though that's a good thing to look at. But you might run into a situation where f double prime equals 0, but the second derivative is positive the whole time, positive before and after that x coordinate that causes f double prime to be 0. It's really when f double prime changes sign. And has a tangent at that point, meaning we're differentiable at that x value. So let's find the points of inflection here. Y prime, of course, is 30x4 minus 15x squared, and derivative of 3 is just 0. Y double prime is 120x cubed minus 30x. Set that equal to 0. Factor out a 30x. 4x squared minus 1. Solve for x. You should get 2 answers. I know I'm kind of skipping the algebra a little bit, but 30x equals 0. X is 0. 4x squared minus 1 equals 0. 4x squared equals 1. x squared equals 1/4, square root both sides, boom, boom, boom. Easy peasy, right? Okay, you gotta do a sign chart too. So you're still doing all the same stuff we did before in the previous page. Still doing all the same stuff. And let me teach you guys how to do these a little more efficiently. I probably could have broken this down further as 2x minus 1, 2x plus 1. And so we have three factors, 30x, 2x minus 1, 2x plus 1. All those have 1 as an exponent on the outside, or 30x raised to the 1 power. So they're all linear factors. You're going to see sign changes at linear factors. If I plug 1 in, go ahead, plug 1 in, it's positive. Now, because 1/2 came from 2x minus 1, and 2x minus 1 is linear, you're going to see a sign change on the other interval. And 0 comes from 30x. 30x, x is a linear term. You're going to see a sign change. Negative 1/2 comes from 2x plus 1. That is linear. You're going to see a sign change. So they will alternate in that regard. So you're, but what if you have like 2x plus 1 squared, let's say? What if you had 2x plus 1 squared? Now that's quadratic. Squaring things never become negative, right? So at x equals -1/2, I would not have had a sign change. In fact, it would just stay positive before, because it was positive before to the right -1/2, and to the left is also. So that's what you can do is a little more effectively. I'm going to take this kind of approach for the future problems we do in this section here. But because they're all linear, leave it negative. So you do have to look, you want to be mindful, or if you have an absolute value around it, that's another thing too. And we're going to do a lot of sign charts in this session here. So I'm going to kind of keep teaching you guys how to do sign charts more effectively. And I have a worksheet, which maybe we could talk about next week. I'm not sure if I'll have a chance to prepare for this week. Yeah, we have a test tomorrow. Now the points of inflection. I abbreviate the points of inflection as POI because I'm lazy. POI. The points of inflection is when the second derivative changes sign. Well, change sign at -1/2, at 0, and 1/2. And that's it. Those are your points of inflection. If you were to support it graphically, we'll look at the graph. Actually, we'll look at the graph in just a little bit because I have a lot going on here. When you justify your answer, or if you're asked to justify it, you don't say f as a point of inflection at this x value because f delta prime is 0. Remember, it's not necessarily when f delta prime is 0, because I did explain what if I had 2x plus 1 raised to the second power, right? Then I don't see sign change there. You really have to say because f delta prime changes sign. So I'm going to talk about that justification just a little bit. One other thing I want to talk about too, you guys might remember back in the day when you had to graph like polynomials in algebra 2 or pre-calculus, and there were like bounces, and you had to like talk about why things bounce. Like for example, you would have a function here, like maybe this is x minus 4 or x plus 4 x minus 1 squared. And you say, oh, because there's an even number here, it bounces. It's because of sign charts, really. If I did a sign chart here just for f of x, I'm not doing a derivative, I'm just doing just simple algebra here. If you did a sign chart here, and if I plug 2 into my function, I got positive. If I plug in 0, it's still positive and negative. That's why you see the bounce in these graphs here, because of a sign chart and because this factor not being linear, being quadratic. Now, if it's cubic, then you are going to see a sign change because it's an odd exponent, and odd exponents can get both positive and negative outputs. That's the reason why. Well, the points of inflection, yes, the concavity and the points of inflection are closely tied, 100%, yes. In fact, when you're doing doing the sign chart for the second derivative, you want to extract both the intervals for concave up, concave down, and points of inflection. Absolutely. And again, let's say we had like x to the 4 power, right? 4x cubed is the derivative, second derivative is 12x squared. So when you set this equal to 0, you get x is 0. You do a sign chart for the second derivative, positive and positive before and after. And here's the graph. And this is concave up the whole time. If you do your tangent lines, the tangent lines are increasing in value the whole time for all real numbers, from negative infinity to positive infinity. So shows that f does not have a point of inflection. To have a point of inflection, you need a sign change at F prime. There's no sign, so you can't just say that. That's bad. Oh, F prime 0, we have a point of inflection. No, you have to have a sign change for the second derivative. So it does not mean there's a point of inflection. That's not sufficient justification. F prime must change sign. You need to say that. Yes, there's a graph still considered concave up. Well, at F prime equals 0, it's just momentarily not so actually you would say you're concave up. Great question, actually. Thank you, Catherine, for asking that. You would say you're concave up from here to here, and you would not include 0. So I should have just said it's concave for all real numbers. The tangents are increasing for all real numbers, but momentarily we're in that limbo. We're not concave up nor concave down at x equals 0. Okay, we're doing great on time. I kind of give out a little sigh here because I don't really care too much about this, but we should talk about it. You guys should know it. So we had the first derivative test, right? And this part's a little confusing. I was confused about this in high school, mainly because I was a bit of a space cadet in high school. And I don't know if I should talk about this, but yeah, so I took AP Calculus when I was a senior, 1995. So that was what, 26 years ago. Speaking about now, age myself. By the way, that's when the 49ers won their last Super Bowl. So yeah, it was a really fun time. Steve Young, Jerry Rice were playing great football back then. Anyhow, what was I going to say? Yeah, I was getting a little distracted. So yeah, when I was in AP Calculus class, it was a large class, large public school in Fremont, and a lot of times we would goof off, and sometimes we'd play cards in the back corner. It's terrible. I shouldn't really share the story with you guys, but the bottom line is that I didn't really pay careful attention at times when this was being discussed in my AP Calculus class. And so when I got to college, I was a little confused about first derivative, second derivative test, and I think I got like a B or B plus my first quarter at UC San Diego when I took calc, because I had to do I majored in chemical engineering, so I had to do a whole bunch of math classes. But yeah, and so I got this stuff confused. And so when I heard the word second derivative test, I thought that what I did right here, all the work I did with the concavity was a second derivative test. No, what we just did right now is a concavity test and looking for points of inflection. Second derivative test is like the first derivative test. Second derivative test helps you find local mins and maxes. But you use the second derivative to help you. So don't confuse what we just did. So when I say second derivative test, what we just did the last few minutes, not second derivative test. That was just a test for concavity, whether we're concave up, concave down, and points of inflection. That's it. A second derivative test is this. So f of 2 is 1, great. F double prime 2 is 0, great. So that means we're going to be a horizontal tangent here. And f double prime 2 is less than 0, so you're concave down. So I'm going to expect the graph to look like this. Because what's happening is that if I draw tangent lines, that's positive, then 0, then negative. my tangent lines are decreasing in value. I will say this though, 26 years ago, AP teaching was a little more old-fashioned or archaic. I do feel the teaching methodology has improved since I became a teacher about 16 years ago, or a high school teacher, I guess, I suppose. But I will say that not justify my poor behavior when I was a senior in high school, but well, I was a good kid, just not paying attention. But I do think we've got better at teaching this stuff, and that's kind of the emphasis now. Is that let's focus on tangent lines. When a tangent line is decreasing in value, that's concave down. So what it tells about the shape of the graph, it looks like this. It's a parabola that points down. Or it doesn't have to be, but I mean, it could be something else, I guess. I don't know. But that could be what we have. So this is the second derivative test right here. If your derivative is 0, so that's a critical point at x equals c. Here we have a critical point at x equals 2. And your second derivative happens to be negative there. That's going to be a local max. I know it sounds weird when you say your second derivative is negative, but it's local max because you're concave down. So you're concave down, that means you're doing this. It's a frown face, or the derivatives were positive and 0, then negative, were dropping in value. If your first derivative is 0, but now you're concave up, you have a local min. I know it sounds a little counterintuitive, but that's a happy face, right? When you're concave up. Or when you're concave up, your tangent lines are negative initially, then 0, and then positive. So you're increasing in value. Or they could be positive the whole time, but you're just increasing value. You're still concave up, and you're going to have a local min there. Now, what do we do if f double prime equals 0, f double prime c does not exist? Then there's no conclusion. About mins or maxes. We can't conclude anything about it. And in that case, just use the first derivative test. The College Board sometimes will actually ask us a multiple choice question. Look at these conditions, like they'll say, oh, if f prime f2 is 0 and f double prime blah blah blah, and they want to make a statement about it. They're really just testing really more the theoretical stuff that's going on here. Question in the chat room. It's up to you. Great question. How do you use the first, second derivative test? It's a preference, whatever you prefer. Personally, I think you guys should just use the first derivative test. But what if you're being asked on an AP exam to do the second derivative test and you have to show it? But yeah, that's why I have to teach it to you guys. Personally, I do the first derivative test, which we did not in the video, right? And I did in the beginning of class. I recapped it. Let me show you how the second derivative test looks in action, and then I think this would be a good place to take a little break, and then we'll come back and do more of the notes here. Okay. So yeah, let's do the second derivative test. So you take your first derivative, 6x squared minus 6x minus 12. Okay, we just did this one actually. Set equals 0, factor out of 6. Solve, or factor, and solve. Now, these are your critical points. So we know that f of negative 2 equals 0. Sorry, f prime negative 2 equals 0. And f prime of 1, sorry, I meant to say 2, not negative 2. My apologies. And f prime negative 1 also equals 0. Okay. Now, this is the part where, again, your teacher who was a space cadet many years back, don't do sign chart for f prime. You're not going to do a sign chart for f prime. What you're going to do next is now take the second derivative. Instead, find f double prime and do a sign chart there. So if I find f double prime, that's easy. That's going to be 12x minus 6. Set that equal to 0, factor out of 6. X is half, and you do a sign chart there. Your second derivative is positive, and you're doing this for the second derivative, by the way. It's positive here and negative here. Okay, question in the chat, or did I make a mistake? Oh, how do we know that f prime equals 0? Oh, that's just because I remember I already factored it, right? This is f prime. I already factored it. And remember, x minus 2, you said each factor equal to 0. That's all. I believe that was your question. Yeah, that's all. Whether the derivative exists or not, that you would need a rational expression for your derivative, which we don't have here. But if you did a rational expression, then just set the bottom equal to 0, and that would be where the derivative does not exist. Anyway, I did a second derivative, 12x minus 6, factor out of 6, solve for x. Saw where the second derivative is positive and negative. So f double prime of -1 is negative, obviously in that interval. F double prime of 2 is positive, obviously in that interval. And then what you could say, and this would be a good place to take a break in about a minute. What you could say is that at x equals 2, we have a local min. At x equals -1, we have a local max. Again, you have a local min because at 2, because your first derivative was 0, so you have a flat tangent line, right? Horizontal tangent line. And because you're concave up, right? X equals 2 is an interval where you're concave up, right? Here's x equals 2. We're concave up. We expect that critical point to be a min. Where at x equals -1, which is in that interval, so the first derivative, of course, was flat, horizontal, and we're concave down, right, like this. And so therefore, that's going to be a local max. There is a formal way of writing this, which is right here. You say f as local max, blah, 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 at this y value at x, because f double prime was less than 0 at x equals. Of course, you would also need to say that f prime of a equaled 0. I mean, that's also true too. And over here, you have to say, f prime of c would equal 0. But I suppose if you're just saying this, that would be the justification for the second derivative test, because you have to use the second derivative to support that this is a local min or local max. That's the second derivative test. So it's like the first derivative test. Your finding local mins, local maxes is the same result. Just the difference is that you're not doing a sign chart for the first derivative. You're doing the first derivative still, because you got to do the first derivative to get to the second derivative. And you're finding critical points because you got to know where local mins maxes could potentially be. But then you're using the second derivative as kind of like the final supporting evidence. Whereas for the first derivative test, you do a sign chart for the first derivative, and you look at the signs where, okay, where's the first derivative positive, where's negative? And if the first derivative changes from positive to negative, that's a max. First derivative changes from negative to positive, that's a local min. And which one you should do, it's a personal preference. It's up to you. I think it's roughly the same amount of work. Maybe, I don't know. Maybe it's for second derivative test is more work. I don't know. I mean, it's up to you. Okay. So I think that covers what I want to do right now. So I want to give you guys a 10-minute break. So we'll come back around 10:28 or close to 10:30. I'll do pages 6 and 7 when we get back. That kind of ties it all together. Interpreting graphs. Sadly, I don't know if we're gonna get to this worksheet again. I might have to, the more I think about it, I might have to make my videos a little longer so I can get to more, so I'm not spending as much time lecturing. Um, but these are good worksheets. It's actually, there's just one problem. You know what? Maybe after I do, the more I think about it now, because it's not too bad of a worksheet. Maybe after I do example 4, and maybe parts, there's no example 5 because it got skipped, and maybe parts of example 6, I can have you guys try the worksheet in a breakout session because they're kind of asking the same thing. Example 7, I might forego, and maybe I might just talk about it next week. And maybe I don't assess you on this particular question. Let's see. Let's take a break right now. Let's come back in about 10 minutes. And yeah, and then we'll do more of this stuff. And I'll actually stop this video and make 2 videos today, one for pages 3 through 5 and pages 6 through 7. So let me stop sharing. Let me stop recording.